So, it's a pleasure to announce the next speaker of this morning session, Florian Girelli from University of Waterloo. And he's going to talk about the 2.0 of something, namely 2.0 of covariant loop quantum gravity.
All right, thank you very much, Hanno. All right, good morning, everyone. So thank you for being here. And of course, I would like to thank the organizers for their kind invitation to speak in front of you today. So what I'm going to talk about is basically, or actually, I'm going to talk about what I was asked to talk about, which is a kind of higher gauge theory. And so higher gauge theory is basically some stuff relying on category theory, these kind of things. It's quite fashionable these days in condensed matter. But today what I'm going to do is that I'm going to focus on what's relevant for us in the quantum gravity regime. And so I'm going to talk about what has been done, and I'll try to also mention what we are trying to do back in Waterloo. So the plan for today is actually to start talking about topological models. You know, I did a lot of work on topological models, so I'm kind of under the influence of topological models. But that's fine, because topological models are also relevant for 4D gravity. And I will recall this fact. So this will be kind of an introduction. And then I will actually give more details, and will show you what are these higher structures that we're talking about. And I'll try to stick to things that you know, so that you actually can follow easily. And then I will conclude with what we intend to do. All right, so let's get started. So the starting point is, like I said, a topological theory in 4D. And so this is a BF type theory. And here I just wrote it in a bit of a, maybe in a funny way, because there is there's going to be there is a T over there. That's kind of the T map. That's kind of is going to be like a Lie algebra homomorphism. This is just a map, and so for example, it could be linear map, it could be 0, then that would just be normal BF, or it could be the identity, and then that would be like BF plus BB, what people call BF plus BB. So if you look at the equation of motion of this action, so you have one, this one that comes up, but you have this other one. And this other one tells you like the T of B is equal to F. So B is a two form, and this relation tells you that the T of these two forms, so we're going to see this like the boundary, is basically related to F. F is the curvature of the connection, and the connection is a one form, right? So it's a data about one, it's kind of data about, it's a 1D data. And so here, this equation of motion tells you that the two form, like the surface information, is going to be related to a boundary information. And that's going to be something that is going to come up a lot along the way. In fact, we can see how this is relevant for gravity. So when we talk about gravity, we talk about Einstein-Cartan with Holst. Then here there is no B field. But we know there is actually many formulations of gravity, and actually many of them involve B fields, right? So for example, there is a Plebanski one where you have Lagrange multipliers to implement the simplicity constraints. You have the Maxwell-Mansouri and the BF form due to Laurent and Artem, which I actually like quite very much, because the theory gravity appears as a perturbation of the topological model, this constant which actually really makes this interaction term here is spawned out by this coupling constant, which is very small. And so you can see gravity as a perturbation of the topological theory. You have the Mikovic-Vojinovic action also, and Evray-Krasnov. And you see that on all these different models, basically, when you look at the equation of motion, so here I didn't write all of them. Of course, for example, in Plebanski, you have the one for implementing simplicity constraint. But typically, what you have is that the two form, right? The two form is going to be related to the one form data, right? So that's kind of, and you see here first the identity. That's like this guy will be the contribution for the topological model, and that's where gravity pops up, right? So we're kind of tweaking the topological model to implement gravity. And so, of course, this is something that is known, right, that we can actually tweak 4D topological theory to recover gravity. Yeah. So this is something that we do, for example, when you talk about spin forms, right? When you want to build a spin form, typically what you do is that you start from a partition function of a topological theory. So you use that as a skeleton, and then you tweak it, you force it such that you can implement the gravity aspect. You can implement the simplicity constraints, for example, for the Barrett crane, APRL, and so on. Let me skip that. However, if you deal with a topological theory, mathematicians actually have worked what are the partition function, or what should be a good partition function for a topological theory in 4D. And there is this categorical dimensional ladder, which basically tells you that as you go up in dimension, basically you should refine, or you have more and more structures to characterize your state sum, or to characterize your topological model. So if you deal with 3D, you can use groups, or actually quantum groups. Those are off algebras, and you're going to use their representation theory, which is just like one category, is the normal stuff that we use always. That's 3D stuff. But then if you go a higher dimension, then you need to add more structures. Okay, and so so that's going to be the thing that I want to argue today, is that maybe what we are actually missing some stuff when we want to construct some spin 4 model or some state sum model. Some state sum models have been actually explicitly constructed for some finite 2 groups by mathematicians. And then there is also the case where with Lie 2 groups, a model that was constructed by Laurent and Aristide, and independently also by Korepanov. So in in 4D, higher symmetries are actually the key symmetries of a topological theory. And so when you build your state sum, you should use the representation theory of these higher symmetries. Okay, that's going to be my point. I want to also talk maybe in a different way. If you look at matter in 4D Minkowski spacetime, right? So you have like maybe some scalar fields, and you have matter in a flat spacetime. So this means that the connection that you're going to use is going to be flat, and then also you want that there is no torsion. Okay, so what you can do is that you can actually deparameterize that, right? So typically you just use Levi-Civita and so on. But what you can do is that you deparameterize that, and you use Lagrange multipliers to implement the constraints. That there is zero curvature, that there is zero torsion. And so then in this way, you get naturally that the theory is going to be coupled to a topological theory, a BF type theory. And I just told you, BF theory, mathematicians argue that BF theories are basically characterized by 2 symmetries, and so we should have somehow, so this 2-state sum that should pop up. So do we have such symmetries in the context of matter? In this normal, I'm talking just about normal stuff, like Feynman diagrams in a 4D spacetime. And then, yes, the fact is that there is, I think, this a very important result, which is, I think, underappreciated by Laurent and Aristide. We show that, in fact, if you have Feynman diagrams, you can recover Feynman diagrams as basically a particle propagating in a topological 2-state sum. Okay, and so in this case, the symmetries that we deal in this case are basically the Poincaré 2 group, or the Poincaré symmetries. So Poincaré 2 symmetries actually even appear in Feynman diagrams, right? So you can also then try to generalize that. Maybe you want to say, okay, I can put curvature in the game. So instead of dealing with the Poincaré Lie algebra, I can deform that, make it De Sitter Lie algebra. And then even if you, so there would be there would be some kind of theory like that, the topological one, and then you can try to implement gravity, for example, through the McDowell-Mansouri type of action. So these are the things that were argued by Laurent and Aristide. So to recap, gravity can be seen like a modification of the relation. When you look at the equation of motion for all this gravity action, they can basically, it's somehow they are relating the 2 form to a boundary data, a 1 form. Okay, and so you can have different, according to the different formulation you're going to choose, you're going to have a different way, you're going to have a different relation. and then two symmetries appear in the Feynman diagrams. And so my point is that two structures basically are naturally present, but we are not really leveraging them. So, oops, I'm going too fast. I spoiled the thing. So now what I want to do is I want to try to give you more details. I keep talking about two structures, blah, blah, blah. What are actually those guys, okay? So now I want to try to talk about two categories. So let's jump into category theory, just like Obelix. We're going to jump into category theory. Splash. Then up. Actually, I'm not going to talk so much about category theory. All right, everything is gone. So in fact, what we are doing is quantum geometry. So I'm going to try to have geometry as a guiding line to understand what's going on. And here I put John Baez, kind of, because I thought he had the same haircut, at least back in the days, he had some haircut like that. But it could actually be Laurent, because Laurent is actually the one also that really pioneered all this notion of two categories and so on into the quantum gravity field, of course, together with Aristide. So let's do that. Let's see what we can do about these two categories. So I'm going to talk about two vector space, two Lie algebras, two groups. Today I'm going to put a lot of twos. Basically, I'm going to put twos in front of everything. All right, but let's start with what we know well. Okay, so what we know well is holonomic flux algebra, these kind of things. So let's start with the flux. The flux is basically a vector that's kind of the normal. It's associated with to a face, right? So that's a vector. And then what I can do is that I can sum these vectors when I'm going to compose these faces. In fact, I can have that the sum of these normals is going to be equal to 0. That's going to say that these surfaces, these faces, they're going to close. And, I'm going to ask that this decorations sum up to 0. So it's like a two holonomy is going to be 0. Here 0 because it's an abelian group. When you discuss about the flux, you can actually check out what's a discretized version of the flux. And it was noticed in two different papers, or two different papers. First, it was by Winston and Alejandro, where they were looking at a string defect, and they noticed that basically this guy could be, the flux could be just written as, when a discretized version could be just written as an exact two form, okay? So then this means that you can actually go to the boundary, and then this means that you can just characterize this flux in terms of a boundary data. You see, this is the thing I was talking about before. You can characterize a phase information by some boundary data. And also this was used extensively in the context of spinning geometry by Laurent and Jonathan Ziprik. So the idea is that we can relate the phase information with the edge information. Of course, this J is not the edge guy, right? It's not the edge vector, because if the sum of, I was doing this sum here, this sum would be 0 because the triangle is closed, right? And I'm telling you that the sum of the j's here, the vectors associated with these edges, is actually equal to x. In fact, the meaning of these guys, these j's are basically the normals of like a Gauss tetrahedron. It's like you could imagine there is a Gauss tetrahedron, and there are normals to these Gauss faces. And what we're saying here is that this tetrahedron is closed. So basically, that's how I can express the j's in terms of the x's. This is something also that was kind of used by Hall and Mushin and Aldo when they were talking about the curved tetrahedron. So what I would like to do now is to revisit this notion, just revisit this relation, right? So here we're saying that x basically is going to be related to these three vectors. And so, as I told you, now I always have in mind that phase information is going to be kind of related to the boundary information. And so what I would like to do is to say, oh, in fact, I could start from J1, J2, J1 plus J2, and x is telling me how to get J3. Okay, so that would be just rewriting this, reinterpreting this equation, right? So I start from J1 plus J2, and I add X, and then I get J3. Or you can say otherwise, see that you can put put a T in front of the X, and T would be the identity map, right? So if T is the identity map, you don't really see it, but really you could have a boundary map, and that said otherwise, that T of X is just the sum of the J's. So you have a boundary map, just like I was telling you before. And so when you do that, here you go. You're actually starting to talk about two vector spaces. So this is a two vector Alabais-Krantz. So there are different notions of two vector spaces. And here that's one that was introduced by Baez and Krantz. So what is a two vector space? A two vector space is actually given in terms of a pair of vector space and a linear map, this boundary map. Okay, so we have, so we can start from so the J's will be like in the V's, X will be in W, and then here in this case, the T map is just the identity map. And so what we can do then is that interpret the W's, right, or the X and the T as a way to encode the transformation that you can perform on the V's, right? So we can say we can start from V, so this guy, and we get the target. It's going to be this guy, right? That's a relation that we discussed before. So we can formalize that a bit and talk about source and target. So we're just organizing things. And so here we have like a transformation. The source is J1 plus J2, and then we have the X. So that's the source, that's this guy. And then the target is going to be J3, and so J3 is obtained by J1 plus J2 and X. So this is basically now we are defining a two vector, right? So that's going to be the data of the source and the phase information. So we have boundary information and source information. Now these vectors, two vectors, we can add them. And so to add them, you know, it's like maybe let's recall how you can combine paths, right? So if you combine paths, you take a path here, another path. Well, if you want to combine them, you need that the end of this path should be the beginning of this path, right? And then you can glue them. So now we're going to do the same with surfaces because these are kind of geometrically surfaces. If you want to compose two faces, you need that the target of this face should be the source of this face, and then you can glue them. And so this is just rewriting this notion of addition that we were talking about before. Okay, so that's basically what I was doing here. So if you talk about two vector spaces, then you can talk about Lie algebras. Two Lie algebras, right? Because what's a Lie algebra? Lie algebra is just a vector space with a Lie bracket. So we upgrade our two vector space to two Lie algebra. And so how do we do that? Well, each of the vector spaces are going to become Lie algebras. I'm also going to throw in some action of one Lie algebra on the other one. And then basically, so we still have the same structure for the source and target. But now what we have on top of that is that we have a two Lie bracket, and the two Lie bracket is constructed from the brackets that you got from the individual pieces here. And this two bracket is going to satisfy a two Jacobi identity. You can you need to put some requirements, compatibility requirements, and the source and the target are going to be compatible with this bracket structure. And so you remember that my example is like the spinning geometry or the Holomy flux algebra. And so here you see that the flux is kind of a SU2 type Lie algebra. And so what would correspond to what the spinning geometry case will be something like that, where we have both SU2 type Lie algebras. All right, so if we have Lie algebras, we can exponentiate them and make Lie groups, right? So then we're going to have Lie groups by exponentiating these Lie2 algebras. And so now if we talk about two holonomies are going to be like maps from boundary holonomies, one holonomies to to the other one on the other side. So really what we're going to have here, like we can say that the L here, which is a surface holonomy or two holonomy, is going to map this one holonomy over there. So we still have the source, the target, that's all this notion is there. We have some relationship between the action and the boundary map, all right? And as a specific example, what I would like to do is to take still as before the case where we're talking about the identity case. So boundary map is the identity. So in this case, what we're really saying is that the holonomy that is associated with this face here is just given by the curvature associated with the connection there, right? So this is like saying I get a one holonomy over there, and this guy coincides with this one holonomy. Okay, so L is that. This no relation here is often called fake flatness, and so I might use that from time to time. So when we talk about the curved tetrahedron, this is exactly what people use. Okay, so that's what really the idea, because of course you can't have just non-abelian holonomies just on the face. So people, when you consider the curved tetrahedron, you naturally said, okay, I'm going to consider the instead of just talking about this flux here, well, I'm going to consider this flux as defined from the boundary, right? So that's basically the idea. And in this case, you have that the closure constraint, the Gauss constraint is just going to be given by the identity, the Bianchi identity, because each guy here is just given by that. And so here what we're just doing is basically doing something similar, or very similar to what people were doing before in the curved tetrahedron. It's just that I have more structure. And my point is that when you define the curved tetrahedron, you were just working with the boundary data. So you were basically, people are solving and solving the constraint here, just working with these k variables. So they were called m's, and they were a combination of these k's. So they were just keeping the group information and kind of omitting this phase information. And the point is that here, really what we have is we have both phase and edge information. And that's what makes a two group. And if you have a two group, then you should talk about two group representation. And so that's kind of going beyond just one representation of a group, because here we really have a two structure. Yeah. So yeah, like I said, this is the idea. This stuff is basically behind all the proposal for the curved tetrahedron. So let's review quickly. So if you talk about the holonomy flux algebra, what you can do, we can just by using Stoth theorem, we can actually introduce this edge variable here, right? So we have x and the j's. And then here as well, right? Because here we can have an arbitrary curvature maybe. And so, but just using Stoth theorem, we can have a phase decoration there. And so here what we are doing, so when you deal with the holonomy flux here, you're kind of dealing with T star of G. And now what I want to do is basically really work with a T star of a two group, right? Some kind of two group. And this is something that we're working on. And so if you have that, then you can generalize that to the curve case, because now you have a lot of good data. And so you can put non-abelian holonomies also on the edges here and on the faces as well there. So this is, using geometry, I introduced you the basic structures. And so now what I would like to do is to go maybe at the infinitesimal level and talk about two gauge theories and make the point of why in BF theories we are talking about these two symmetries. So when you deal with these two Lie algebras, you can also construct a gauge theory from these two Lie algebras. And so now you're going to have a bit more information. So typically for one gauge, you just have a one connection. That's a one form. But now we're going to have more. We're going to have a one form and a two form. Okay, so then you can construct the curvature data. And so when you want to do curvature, you have D, you use the differential, right? But now we also have the T, right? You remember the T, introduce the T was kind of a boundary data. So there is a combination of D and T. And so that's why now the curvature data on the one side is actually given by the F, but also by the T of sigma. And then you have the curvature for the two forms, the sigma here. So that's going to be a free form. So that's the curvature data for this connection data. You can introduce gauge transformation and two gauge transformations. So normal gauge transformation, you have the fiber here. That's a normal principal bundle with a normal group. But then what you're going to have also is gauge transformations associated with a phase here. And these, they are parameterized at the infinitesimal level by scalars in the Lie algebra G. And now these guys are going to be characterized by one forms in the Lie algebra H. And what's really great is that, when you define a gauge transformation, so here you recognize a normal gauge transformation. So it's a D of alpha plus the bracket of the connection with alpha. Right, in fact, when you look at these two connections, or a pair of connections, right, here if you want to look at how this guy is transforming under all these transformations, that's going to be all that we're going to have the D of the parameters plus a bracket, but now it's a two bracket, right? So the two bracket encodes, you know, both the one gauge and the two gauge transformations. So these guys are transforming, the A is transforming as a connection. What about curvature? You know, curvature typically transforms well, right? Connection transform as connection that don't transform well, but curvature is a tensor. It transforms typically under the adjoint or coadjoint action. And so here that's the same. This bracket here, there's a two bracket. You can use a two bracket, and the two bracket basically allows you to encode with the transformation of this form data, the curvature data that you had over there. And so the shift symmetry, you might have seen that here there was a shift symmetry, right? The translation here by parameterized by phi, when this shift symmetry is actually encoded by, is also encoded by these two brackets over there. So I find that quite, you know, it's like what I said earlier. What you do is you normally with bracket, with one bracket, come the formula follow nicely when you go to the two level. So if you want to, you could try to say, okay, let's construct an action. And I want to implement that I got zero curvature. So it's like a BF type theory. It's just that now I've got these two curvature data. So I'm going to use Lagrange multipliers, B and C. So this is like a 2 BF theory. So I got Lagrange multipliers. I know curvature transforms well under the two adjoint action. So the B and C should also transform well. And I'm going to use a bilinear form which is invariant under that, so that, you know, its transformation percolates well. So I can look at the canonical variables, and then in this case, we see that we have configuration variables are the 1 and 2 connection, and these guys are dual, so that's one form and a two form. And then you can also realize that I can shift also this B, right, and then use the Bianchi identity. And so there is an extra set of symmetries. And so then this means that, in fact, what I've got, I'm going to have like a cross, a bow tie, let's say, I forget the name now, of 2D algebras. So in fact, what I can do is that I can repackage this type of symmetries. I just add a boundary term. It's like a change of polarization. And just by adding a boundary term, I can just recover and rewrite this kind of 2BF theory that I had before as a standard, as just a normal BF theory. So BF theories are characterized by two symmetries, right? So here you see, if you look at the configuration variables, there's going to be a one connection, and the one connection, those are the configuration variables, just like you would do in a standard BF theory. So let me skip that. So if you were discretizing this, you know, you could start from normal, you know, SO31 BF theory. I don't put any BB interaction. And then in this case, if you were to discretize, you would discretize that as normal gauge theory. So you would have, you know, holonomies, SO31 holonomies over there. And then dually the flux would be SO31 star, which is just R6. So you can discretize it like that. And then what you can do, though, you can have another discretization, just the same thing as I was this flipped, change of polarization I was telling you before. And in this case, you're going to take some of the holonomy that was there, you're going to send it over there. So you're going to keep, I'm going to break SO31 into SU2 and AN2. I'm going to send in AN2 over there. And I'm going to take some R3 that was on this face here. I'm going to send it over there. Okay. And so now this is really like a two BF theory. This was like maybe a one gauge theory. This is going to be really a two gauge theory. So now this is, you know, discretization of the same guy, same action. And so then you can argue, if I look at the partition function, now if I look at the partition function, this is a topological model, so I can associate this partition function symbol. And so you could expect that the symbol should be related. So the symbol defined for one gauge should be related to the symbol for a two gauge. In fact, this was shown that it was the case by Laurent and Aristide for some specific example of a two group. If you try to put a BB interaction term, then this is a place where you cannot really use one gauge theory. You really have to, you're stuck, you really have to get two gauge theory, because if you were to discretize, when you put BB, it's kind of equivalent to trying to put the flux, to deforming the flux on the face, but you can't have the flux over there. As a non-abelian group alone, you need some edge information, so you need to break it up. And so this is when you put the cosmological constant in the game, that's where you really see that you really need to deal with, to my mind, with two groups. Let me talk about now two representation theory. I'm not going to say much because that's quite involved. And what you could do now is, I told you that we have in mind to extend this notion of spin networks, right? So by you just using stock theorem, we're trying to extend that. And so you can try to construct the functions which are gauge invariant, 1 and 2 gauge invariants by, you can do some averaging. But then you can try to say, okay, let's do a Peter-Wald theorem. Let's try to see what are the spin networks. Let's write this in terms of representation theory. And the point is that for two groups, that's a bit of an issue where we lack a Peter-Wald theorem. We lack this Fourier transform. In some cases, you can also discretize the partition function very nicely. It's pretty straightforward. And so you just get, it's a natural form. You get a delta for the face information, that's like a fake flatness here. And this is just like the Bianchi identity kind of delta over there. So this is a discretization of this BF theory, 2BF theory that I was mentioning before. And in fact, what we did with these guys is that we actually constructed a 2GFT, so a GFT, a group field theory, built on two groups such that the Feynman diagrams were associated with that. But then you would like to construct a state sum model or two state sum model out of that, and that's actually hard. And because we don't know the Peter-Wald theorem. In fact, you see one way to deal with that is actually to talk about characters, right? Typically, we talk about characters to do this. We write the delta in terms of characters, but we actually don't have a good understanding of what's character theory when you deal with two groups. I should say that there is one case where we actually managed to do that, and there was some work with Seth, Bianca, Aldo, and Peter, where we managed to, for the fourth simplex, we managed to look at Laurent's model and relate it to a discrete partition, the discretized partition function of a BF theory using geometry. So we didn't use the Peter-Wald theorem, we actually just used geometry. So here there is actually some nice math that is missing. So people are working on that from a Konosmara perspective, I think. But here we're also working on that. And I think with respect to these guys, we have a head start because what we know is that we're working with gauge invariant quantities. So we kind of, we gauge average or two gauge average. And we know that if we do a Fourier transform of that, we should recover the constraints. Okay, so we actually have some guidance from geometry. And so I think that's a useful hint that maybe mathematicians don't have in mind. To make things, of course, it's 4D, so things are never simple. There are actually different notions of two vector spaces. There is an historical one, which came from the notion of categorifying the notion of vector space due to Kapranov and Voevodsky. And that's what typically people use in Konosmara, but that's because they're typically using finite groups. And then Laurent, John Baez, and Aristide, and Derek Wise, they actually built up on that and extended that to Lie groups. And so they have an improved version of that. But then there is another notion that's of vectors, two vector space. That's the one I actually introduced there. And so for me, it's more natural. In fact, you see, if I was asking you right now, what is, if I give you a semi-simple Lie algebra, what is a representation of it, right? What's a representation? Can you give me a representation of a semi-simple Lie algebra? Yes, the adjoint one, right? The adjoint one, you can always represent the algebra on itself. And so the bracket gives you the bracket gives you the nice properties. And so if I ask what is a natural action of a 2 Lie algebra, a natural representation of a 2 Lie algebra, well, then I just introduce the adjoint representation as well. And so, but then I need to represent the algebra on itself, and then it's about the algebra, the 2 Lie algebra is a Bayes-Kranz type vector space, so it seems to be, I like it like that. I'm trying to work with this type of two vector space. I mean, we're going to see what happens. Maybe they could be related, and maybe they could be related in the future. It's just that at this time, it's not clear what's going on. And to give you a further sense of what's going on, so if I use a Bayes-Krantz, what is a representation? Or in fact, what is a matrix? You know, a representation is basically writing the group element as a matrix. So what is a matrix, right? So when I deal with a two-vector space. Well, a two matrix is given by two matrices, right? Could have expected that maybe. But there's actually a third guy. There is also A, so there is an homomorphism. So that's a guy that's telling you how to move from V to W. So the set, the object, right? So like this, I remind you, this guy was the edge information, and this was the face information. So there is this map. So when you talk about two matrices in this case, when you use a Bayes-Krantz thing, and when you use this other two vector space, things are probably a bit different. So when you deal with this type of matrices, you see that here you have the M, little m is going to be a matrix on V. So it's an endomorphism of V, right? So this is the normal matrix. And so what I'm saying is that when you want to deal with a two representation, well, it means that what we want to do is not only consider this guy, which is a normal thing that you would do when you consider just groups, where there is some extra structure that pops up because you have this morphism, this W space, this axis. And so you have more structure that appears. And so I think my point is that I think we are kind of missing that when we don't consider really the two representation of the two groups, especially when we build a state sum model for 4D topological theory. And so two matrices, if you look at the two matrices which are invertible, there is actually also a notion of two group. These guys, they form a two group. And like I said before, the two adjoint action is, you can really encode this guy through this matrix. So let's wrap up. And so let's make a roadmap. What are we actually trying to do? Well, we're going to put twos a lot, right? So you see that here, this is 3. This is a topological model. And so typically, when you deal with a gauge theory, and in 3D, the kind of excitations are given by spinning tops. And so then you can try to use these spinning tops to, to construct the phase space of a polygon through the coadjoint orbits. And then you recover, you can relate that to intertwiners, you can quantum state of a polygon and so on. And so what we are trying to do now is to extend that to 4D. And so now in this case, the natural excitation for topological theory in 4D, that's going to be, we're going to still have a point-like defect, but also string-like defect. In fact, in the talk yesterday by Xiaoyin, also she was talking about string defect, so I think that is kind of probably a good relation there. So then the idea is to try to reconstruct the phase space of a polyhedron, really using these two coadjoint orbits. So just not using one group data, but I want to really use the two data. So I'm going to start with the 2D algebra, and from this 2D algebra, build the coadjoint orbits, the two coadjoint orbits on this 2D algebra. So this is really doing like something similar to Kapovich-Milson, and this is not really like doing Minkowski theorem, I would say, which says that a polyhedron is like a polygon. And then like I said, we're trying to work out what's going to be the two intertwiner in this Bayes-Krantz case, because of course, if you use the other notion of vector space, this was also introduced by people. And so then we can try to construct a spin-4 model, and the one that I like very much, I think is this one, the BF1, based on the Laurent's work on the Magdewell-Mansouri action, because really this one is, we can use perturbation theory, and there is not even a simplicity constraint to implement, so that's really for work in the future. So to conclude, my main message is that topological models in 4D have two symmetries. And so if you talk about two symmetries, you should have two representations. And so therefore, the state sum model should be a two state sum model. And I think we are not leveraging that when we build our quantum gravity models, because we are using state sum models to as a skeleton to try to build our quantum gravity model. And I think that we are not really taking advantage fully of these two structure that is actually present. In fact, they even appear in these Feynman diagrams. And so I think we should really leveraging them. And I think what we are doing now is like we are in a house, and we've been working always in the first floor of the house. And I'm telling you, there is actually a second floor, pun intended. There's a second floor, and you should go up and take the stairs and go up and try to explore. And maybe there is a better view to see what's going to be the quantum gravity regime. I don't know. All right, thank you very much.
Thank you, Florian, for this inspiring talk. We have time for a few questions, please, or comments. Please put up your hand. I see one hand there.
Thank you. Thank you for the nice talk. It's really interesting from my point of view. But I'm a bit confused in one point. So the link between this formulation and the, I mean, the historical formulation in which the higher category appear in the like TQFT formulation. So, I mean, in the scheme you showed at the very beginning is the scheme of the essentially the extent TQFT. So when you want to deal with objects that have a lower dimension with respect to the one of your theory, you have to deal with higher category. But the top form, so the top structure, remain the same. In this case, seems that the top structure changes. So what is the link between this usual structure and the ones you presented now?
What do you mean usual structure? So here I'm just telling you that this is just normal 4D BF theory. And so I just have two symmetries. So what do you mean? So you're wondering how to reconstruct a state sum?
For example, in extended TQFT, the higher category, so the one category, appear when you want to include corners in your formulation. In this formulation, seems that the two representations, the two groups, appear without the appearance of the corner structure, for instance.
So I don't need corner structure. So I mean, what I could say maybe is that what I'm presenting things from the field picture, and then what you have to, so then you can discretize, and then you have to write that in terms of a state sum. So typically, I think the models you're talking about are built on really categories, so state sums. And here, so what I'm doing is that I'm having groups, right? So then I need to do a Fourier transform. I need to implement the Peterval, like use the Peterval or implement some Fourier transform. And so typically the Fourier transformation is going to dualize things. Like 1D is going to be dual to 2D. And so that could be the way to change the dimension that you're worrying about.
Okay, thank you.
Laurent, please.
Yes, I have a question. So first, thank you for this very nice presentation. It's a difficult subject and you make it simple. I cannot agree more with you. First, let me make a remark that, gravity, it's not enough to just have the flux. We need to have access to the frame field. And yeah, I mean that you said it very clearly. We need to put the second stage. The second stage is really where the metric comes in. It's unavoidable. So I'm glad you're pushing that. Now I have a question about these two vector spaces, like the Kapranov, which leads, and it's true that, as you mentioned, one is kind of simpler, where two matrix is just two matrices, where the other one, a two matrix, is a matrix of vector spaces, which is a little bit harder to deal with. So then you mentioned that you get, so you get in the first one, you get what we did, or the mathematician did, the Krenieter type TQFT. And then in the other one, you get this generalized BF TQFT. But you mentioned some connection between the two. So are they like completely inequivalent TQFT, or is there some correspondence between the two?
Between the state sum that you build from Barrett crane,
the Krenieter, yes,
Barrett cranes. So at this time, there is no really relationship, and I think there are not some. Most models are currently defined using the KV, the Kapranov-Voetsky two-vector space.
Okay.
And so people don't really leverage that, and they don't leverage they don't really work yet with the Bayes-Krantz vector spaces. And so the relationship that I mentioned, I think that's the one that you got, which is basically when you use the Kapranov-Wojcicki two vector space, then you can try to relate them to the symbols that pop up in Barry Crane or craniator, undeformed craniator for Poincaré group, for example. But at this time, there is, like, my road was actually diverging because these are different structures, and it's not clear at this stage whether they are really equivalent. So there is a bit of an ambiguity there, and maybe the roads are going to match up later on, but at this time, it seems that the structures are very different.
Okay. So even, let's say, the level of the two spin networks, you would have different labels?
Yeah, we could have different labels, yeah. Okay. But the point is that your construction is really tailored to skeletal, so cases where the T-map is 0, and so you have continuous cases. Here, what I'm going to get is representation of SU2. So in my two vector spaces, so I didn't go much in representation theory, but my matrices are going to be encoding representation of SU2. And so I'm going to use representation theory of SU2. So I'm going to have really SU2 spin, labels, SU2 representations. And so whether this kind of structure are going to be equivalent, I mean, I don't, for me, it's a bit unclear what's going on here. We have two different notions of vector spaces. One is natural from one perspective, another one is natural from another perspective. They are very different. What's going to happen at the end, that's the future will say.
Last question, Jurek.
Thank you. So I'm sorry, this is a non-expert question. I have no idea what category theory is. Loop quantum gravity relies on some construction which is assigning to edges a group element. And we have groupoid of edges, and then we have this homomorphism between this groupoid of edges and group. So it's natural to imagine that we could try to define something, generalize it to two-dimensional surfaces. Yes. That we have, for instance, groupoid of squares.
That's exactly that.
And then so is it?
That's exactly the concept.
Is two category the right tool?
That's right. Exactly. That's exactly the
right thing.
Okay.
So then, what is the group? I guess this will be some
two pair of groups. It's a group is made of two groups.
Mm-hmm.
It's a pair of groups, and you have a group on the boundary and a group on the face.
Okay, so what are those groups for?
So here in my example, they were both SU2s or both R3s, right? So in my example, but then you can have different cases. So here you see that my X here is a R3 element, and the J's here are 3 elements. And here H is going to be a SU2 element, and G is going to be SU2 elements. So these are R3, the normal R3. But you see, when you do flux, you actually put an X on the face. So you're putting a group element on the face. So you're already actually doing that. And when you compose faces to define the Gauss constraint, you're actually composing decorated faces. So you're actually already doing that. It's just that it's a very trivial groupoid of faces because there is no edge information and because decorations are abelian. So you don't care. But as soon as you get non-abelian decorations, you need to be careful. And typically, one way to be careful is to put edge information. And Laurent was working, for example, with a case where you have non-abelian decoration on the edges, but you have abelian decoration on the faces. Like it's the two Poincaré group, you have Lorentz transformation kind of there, and you can have translation on the face. I mean, that's
very good.
Okay.
Thank you.
Thank you very much. So we have to stop here. There will be an announcement from the organizers, but first let us thank Florian.
Thank you.